Swayam Prabha. Digital India. Educated India.
Okay, so let's understand a little bit more about this ARM technology now. So, this Texas Instruments has developed this, ARM Cortex M4 series MCUs, which are like quite popular for a lot of industrial kind of usage and applications. Okay, some of the usages, if you go to the datasheet, you'll find their gaming interfaces and a lot of these some mobile chips we may have say additional chips as these controller chips and things like that. Okay, so there are many devices in which you will find this kind of and then the application note will give these more details. Maybe it okay, maybe not now, but maybe we can go through some of these details in the data sheet. But maybe we can get first like an overview of this technology itself, and then maybe we can go into little more details of the data sheets of this. Okay, let's do that first. Okay, not jump into say. So this ARM technology has a lot of these different you can just kind of appreciate for now that this technology has a lot of families of microcontrollers which are used in many different kind of industrial applications and devices. And the main kind of a crux of this technology is this ARM stands for this Advanced RISC Machine. Okay, RISC. The RISC stands for Reduced Instruction Set Computer. Okay, so this is reduced instruction set computer is having the main idea, okay, or main philosophy here to develop this kind of a technology is to reduce the number of clock cycles required to execute whatever instruction is to be executed. That okay, each of the instructions that you execute, say you want to move some contents of one register to other register, it takes some finite number of clock cycles. Now these clock cycles determine how much is the time taken for execution of the command, and clock frequency would determine how fast that will happen. Okay, so if you have say 80 megahertz kind of a clock, okay, which is there in TIVA, and say you are taking 15 clock cycles to execute some command. Okay, so you can find out what is the time taken to kind of execute that kind of command. Okay, so as compared to the normal microcontrollers where this ARM technology is not there, and when this ARM technology is there, each of these commands whatever are designed in this ARM technology, they will have the reduced number of clock cycles to execute. Okay, so that's why this they can do really fast kind of execution of your hardware programs. Okay, so that is the main kind of advantage of this ARM technology, and it is some kind of an industrial standard now, for a lot of industrial machines, okay, mechatronic systems. This is people are using this ARM based controller. Okay, and the other thing is that the programs that you write, okay, here, even if now the chip is upgraded here, you'll execute those programs with not much of a modification. Okay, so here again the programming is also based on the base C level programming. Okay, so we'll see what kind of ways, how do you kind of really go ahead and program these. Okay, So let's move on to this. These are different technologies and corresponding features of the technology. Okay, so this is a Cortex M4 kind of a technology, and now more kind of a modern is Cortex R4 technology. Okay, so there is some kind of more details are given. So this is what is this architecture. So this is version 7 V7M kind of architecture. So V7R, some differences are given. We may not understand everything at this stage. It's okay, but one can kind of see there are some things that are there in the advanced say for example cache memory is there in this Cortex R4 series, but not there in this earlier series. So as people use this, and then the demand, the manufacturer demand that okay, oh, we want some kind of this feature, people start developing the companies start developing the next versions of the microcontroller, and that's how there's the evolution of these different microcontrollers takes place. The way you see the evolutions that happen in your computer systems. Okay, similarly there are these kind of evolutions that happen, some developments keep on happening. Okay, so the microcontroller that we will be using or we'll be looking at is this Cortex M4 kind of a series microcontroller. Okay, and it has this 32-bit kind of architecture. Okay, 32-bit data processing will be there. Okay, so one can look at some of these details. Some details I may also not be able to kind of tell you detail. I'll have to kind of read more about it, and I'll be able to tell you. But you can try to kind of find out and see if you can understand some of the parts at least. Okay. Say for example, interrupt latency here is 12 cycles. Here it is 20 cycles. It will have some kind of a delay in the interrupt coming in execution. Okay, so this is increased here because of some advanced processing, something like that may be there, which is I don't think this is a good thing to happen. I mean, we want interrupts to kind of get executed very fast. But anyway, so as I said, this is typically these are the features that are given, and some advanced features will be there in the higher series. We from mechatronics perspective, we may or may not need to kind of get into too many details about this anyway probably. Okay, so unless very specific application comes, we should be able to kind of dig into that and see. Okay, otherwise we probably from mechatronics engineers we don't need to really bother too much about. Okay, this floating point unit is there inside this Cortex. So this is one can appreciate that okay, you have this floating point built-in kind of a unit, and here it is single and double precisions are also there. So these are more precise kind of calculations can be done with Cortex R4 series than M series. Okay, fundamentally so even if you don't know in the specific data sheet of the microcontroller, as long as you know that okay, it belongs to this Cortex M4 series, it's fine. You know that okay, it cannot do the double precision as a built-in in the feature in the microcontroller. One has to write a separate program. That means one has to expend more kind of a number of clock cycles to execute double precision in the single precision inherent microcontroller platform. So those are kind of things one can see from mechatronics perspective. So now if you come to this TIVA ARM Cortex microcontroller, its features if you see in the data sheet are given in this kind of a format, and then there will be some block diagram to kind of explain these more in detail. Okay, so you have this 80 megahertz operation. So this 80 megahertz means your clock is running at that kind of a frequency, and then depending upon what is the length of your program or number of clock cycles that your program may take, you can have a sampling time which is more or less based on this. This can determine your sampling time actually. then some memory details are there. Then there are communication details there, and there is a see what from mechatronics system perspective is more important for us is this advanced motion control. So they have these PWM interfaces, okay, two modules each with 4 PWM generators. So there are 8 PWMs in this microcontroller, and for total 16 PWM outputs, and so 2 PWM modules each with 4 PWM generator blocks. Okay, so actually it should be 8. I don't know why they are calling this 16 PWM outputs. So there may be something more we need to see in more details here. Then there are these 2 quadrature encoder interfaces modules. Okay, the encoder which is having A and B pulses. Okay, so that encoder can be now directly connected to this quadrature encoder interface. Okay, you remember why it is called quadrature? Because it's let me think about. Yeah, it gives like these A and B pulses which are phase shifted by 90 degree, and the combination of that gives over one cycle 4 different pulses can be possible. So 4 it refers to the quad. Okay, so that's why it's called quadrature. 4 different pulses you get over one cycle because of this cascade of like 2 A and B signals by shifted by 90 degrees. So that phase difference is what gives you the direction also. So that's how this entire thing how to read these pulses and convert them into count, and increment the count if it is direction positive, and decrement the count if it is direction negative. Everything is done by this dedicated interface. So you don't need to kind of do any of the operations of this more this kind to get the number for the encoder count into your microcontroller system. That will be directly given by this. If you configure in this interface appropriately, you will be directly getting the output reading, and that's what we'll do. We are sending you this motor and along with its encoder. So we'll interface this encoder with TIVA and see how it can give these counts. That all we'll do as a part of the lab. So we'll focus on this motion control kind of a part, and then some part of analog inputs. Okay, and so these other things are useful, say package, and other things will be useful from if you want to kind of now build a dedicated kind of a embedded system board for your application. Okay, which we will not have opportunity to do in this course. Okay, we'll have to do a PCB manufacturing for that, and it's not a part of this course. Okay, so we'll move on from here. This is more details about the diagram. So this JTAG refers to a communication interface which is typically used for downloading the C-level program compiled version to the microcontroller memory, and exchange the variables from the memory to this kind of this software program in which you'll write the codes. Okay, which in this case will be Code Composer Studio. Okay, so there will be some interface that is needed. Okay, which will share some kind of a memory locations to real time know what is happening to different registers, what is happening to different variables in what you have used in program. Okay, they all will be exchanged through this kind of a interface to your computer system to be displayed on your desktop, so that you'll be seeing you run some program in microcontroller, and you see when I execute this command, this happens to this register. All these things you can see on the thing, and also you may be able to register the say if you want to record some signal in time. Okay, you'll be able to do that through this such a kind of interface. Okay, so this is a JTAG or SWD. Those kind of interfaces are there, and then these are different. You can see this bus system is there, and then these are memories that are interfaced. So say some part it will have a unidirectional, some part it has a bidirectional memory. Then there is some so this is like the interrupt vector interrupt kind of interface. Then like that you just read, some part may make sense, some part may not make sense, it's okay, doesn't matter. Okay, so part which doesn't make sense you will go through and read a little more, and things start making sense. So there is a ROM in which read only memory, if you know, I'm sure you know. It has some driver libraries. Okay, so it has you see, this ROM has bootloader. That means the system boots for this microcontroller through this ROM. The way when you start your computer system also, you'll have some kind of a small part of the program that will get executed, that is written in the ROM, so that your system is at for the first time it starts booting from there. Okay, and then it calls off other routines to kind of execute and get the computer ready for you to kind of work. The same way it happens in microcontroller, it starts off with the execution of these commands in the ROM, and then the microcontroller is ready for your programming and things like that. The important part is that there are drivers libraries already recorded into this ROM. So those libraries are not kind of fetched and burnt separately through this JTAG interface. They are kind of taken and burnt here every time the program execution takes place. So that saves you a lot of what you say, programming time partly, and also the execution time. Okay, so the memory of your application will not have any of the libraries files there. Okay, because they are already coded into this ROM, and they'll be kind of called from the ROM to be used. And that is one of the other reasons things are fast in some sense in these microcontrollers. Okay, especially the programming is fast. You will find, okay, very quickly this program gets loaded onto this microcontroller, and now you are ready to execute. Okay, when you start programming, you notice this difference, as compared to what you are doing with XCP100 or your Arduino or in the previous thing. You'll find that the program will get very fast downloaded onto this microcontroller platform, TIVA platform. Okay, again here also, as I said, for the way it was there for XCP100, if you see the pins here, these are GPIO pins. Now this is a general purpose input output, or one can understand this as a digital input output interface. So they have alternate functions. Okay, so this is important to know that pins can have alternate functions. So for example, here if you see this PC4, PC5, PC6, these are the pins here. They have they are shared between this phase A1, phase B1, and phase or index 1. Okay, so these are the pins for the encoder interface. You remember that we had A phase, B phase, and you had index pulse also. Okay, so these pins, so when you interface your encoder, you'll use these 3 pins, or there are 2 encoder interfaces. One of the interface is this, and some other interface you'll find for a 2, IDX2, PHA2, PHB2, like that. You may find some other pins. Okay, so in this case, they fall as PC. So these are the names of general purpose input output. PC6, PC5, and PC4. Okay, these pins you'll connect to your encoders, and then you hope that you configure this appropriately. So naturally then there'll be somewhere you need to kind of say that I'm using these pins not as general purpose input output, but I'm using these pins as encoder outputs. Okay, so that configuration, reconfiguration of the pins need to be done somewhere. There will be some commands to do that. Okay, so this is how one can understand, by looking at these pin diagrams or some other kind of details, what it means when I start programming. Okay, in programming also it will be given there, but if we know what we are looking for, then it's much easier to find out what we are looking for and then figure out and go ahead with programming. So so there are it's a skill, okay, I would say, to develop, and that comes through your previous background of whatever microcontroller programming, and you start programming a new microcontroller, use some philosophical ideas, and then some of these cues from somewhere, or some previous examples of some programming, and you need to kind of finally make sure that your application is running fine. So that is exercise we all have to go through. We'll understand a little more about this Cortex technology. Okay, so let's see, it's maybe 1 or 2 more slides to go through. So this will talk a little bit at a philosophical level about the programming. This is important, and see, once you have this philosophy firm up in your mind, then actually what to expect, what not to expect is very clear. You don't I we don't need to learn syntax. Okay, syntax is not a big deal to learn. Okay, so you might have we might appreciate that by now. We might have learned 2-3 computer languages, C or some other kind of thing, and the syntax is not, but ideas and the philosophy, or the way of doing things, or way of thinking. Okay, how do I create a logic around this? Okay, that is what is more important. Okay, so we need to shift that for microcontroller programming. Okay, the way you think in the domain of normal computer programming, C language programming, although there are a lot of similarities, but there are some certain distinct features that one needs to be very clear about. Okay, so we will not talk about much about assembly level program. We will not use it at all actually, but this is the most fundamental way to program stuff. Okay, so you know all the register details, and you say, okay, for this command to be executed, I know I need to move something from this register to that register, from then I need to do something like that. You need to know the sequence of operations to be carried out, and you are programming each of the operations for just doing some simple task. Okay, that is too much of a drudgery. So that nowadays is all done by the libraries. So libraries will do this task of whatever is to be done to get your interface working, and your task is to now know the libraries, how to use those libraries, and how do you make sense of different things that are there in the libraries or in the register level programming. So suppose we are doing a register level programming. Okay, so see, one of the ways is the most kind of a basic way is assembly level programming. Then little higher than that is in this register level programming, in which you are, so in the assembly level you are actually writing assembly code, you are not using C. Okay, so actually C programs finally will kind of convert the code into assembly level only, but you are directly writing that. Okay, but that is not the way I've just listed it just for the sake of completeness of this, but we'll not use that. So the next higher level programming is where you have the registers, and each of the registers their functionality. Okay, the functionality, how do you know the functionality? Functionality will come from the data sheet in the programming of XCP100, for example. Okay, so for programming say digital input output interface, there is a register called DDR. Okay, the data direction register. Okay, DDRX or DDR whatever, A, B, C, D, there are different registers. Now these registers, you need to write something okay in those as some data, and that will have some meaning, and what data written has what meaning is given in the data sheet of the programming for that microcontroller. And that's how you initiate different registers to achieve different things. Okay, for example, in XCP100 specifically, to have those registers as output registers. Okay, so I want a register as a port, as an output port, then I use DDRA to be equal to some FF number. Okay, so then all the pins of this port A will be configured as a output pins. Okay, in other cases they can be configured as input pins as well. Okay, so like that you write these as a C level commands. Okay, so this DDRA is equal to 0xFF is a command in the C that you will write, and when it is compiled, it will, like, do all these jobs about whatever it needs to be done to at assembly level to get the, make sure that this port A is configured as a output port. Okay, so that is, so there are these registers are called control registers, and then there are some other registers called data registers. Okay, so you need to understand that functionality of this register. Okay, is it a control register or it is a data register, and write appropriate kind of values according to the data sheet in those registers, and your programming is done. Okay, so that's how you go ahead programming next level of program for microcontroller. Okay, where you have access, you are directly, like, writing these registers in some sense. Okay, and so let us see. So this is next level of, like, programming, where you are doing the register level programming, control registers and data registers separately. You are initiating and doing some kind of operation. So some of you are familiar with XCP100. It will be kind of a very easy thing to understand. For those who are not, like, you'll need to kind of see those things and see the data sheet, and then you can make sense of some of the things. Okay, so the idea here is not to kind of, like, understand everything from all the details. No, what we want to kind of, like, get the point here is that you have these registers names available as a variables, and those variables are initiated to some kind of a data values depending upon what is the functionality that is needed. That is one higher level of programming for microcontroller. Okay, and then there is yet another level of programming where you are now heavily dependent upon the libraries. Okay, so there are commands that are there in the libraries that kind of carry out the operation that you want to do, and you have to kind of supply those functions some appropriate data as arguments. Okay, so that is a way, like, the TIVA based or, like, ARM Cortex based microcontrollers will be programming in that kind of a way. Okay, so we'll get into more details about that as we go along, but for now maybe we'll stop here. We have some more details about the programming philosophy coming up next. Different kinds of things that we need for, specifically for our mechatronics kind of application from the microcontroller. What we should have in microcontroller, which we'll use for mechatronics purposes. Okay, so that's what will be coming up the next. Okay, and that's how we'll move on. Okay, so maybe we'll stop here for now.